Welcome back. We got a maze of stuff for you. It's going to be amazing, trust me. We are going to summarize all of the reactions we did on alkyl halides. So reactions of alkyl halides were mainly classified into three groups: primary, secondary, tertiary. Then we also said each of these classes is going to react differently depending on the reagents, and we classified the reagents and put them in 4 buckets. One of them would be the strong nucleophiles that you can see here. The other one was a strong nucleophile that could also act as a strong base. Then we had strong bases that really couldn't act as nucleophiles. And we had weak bases and weak nucleophiles. So the weak base, weak nucleophile, it would be for the same molecule. All right, let's look at some of the strong nucleophiles. We had lots of them. I have just taken a few examples here, and I've listed them according to their reactivity in a protic solvent. And you can see that the bigger and the more anionic ones are on the top. The smaller, harder anions are at the bottom, and they're not very nucleophilic. Now, some of the nucleophiles can also act as strong bases, especially if they have O minuses or nitrogens in them. So they would have a common class. The strong bases that are not nucleophilic are typically very sterically hindered bases, or they could be like hydrides. Even acetylides could be strong bases, DBU, DBN, and so on. And then the weak bases and the weak nucleophiles are basically solvents, solvolysis, water, methanol, ethanol, any kind of alcohol, isopropanol, whatever alcohol you have out there. You could even have acetic acid, and you could also have very, very weak bases and so on. All right. Okay, so let's look at some of these strong nucleophiles. You can see SH minus, SR minus, I minus, amides, then triple bonded carbons, cyanides, acetylides, hydroxyls, and then alkoxy groups, RO minus like methoxy, ethoxy. Then you get to the more like weaker or medium nucleophiles like bromides, ammonia, SR2s, and so on. And then the weak ones like acetates and chlorides, and in protic it would be fluorides. However, if you have aprotic, then fluorides would be better than chlorides, chlorides better than bromides and iodides due to hydrogen bonding. So let's take a strong nucleophile and see what would happen in a primary, secondary, and tertiary environment. That's what we have here, A with primary, A with secondary, A with tertiary. Okay, so that's how this table is arranged. Then we would take a strong base, strong nucleophile, and these would be your small oxygen minuses. Sodium hydroxide, you've always learned was a strong base. I mean, Gen Chem, that's pretty much what you use, potassium hydroxide or sodium hydroxide for all your titrations and so on. So those strong bases are also strongly nucleophilic. So we have a molecule that can act both as a base and a nucleophile. So you can see your methoxy, ethoxy, hydroxy, and so on. So that with primary, secondary, and tertiary. Then we are going to do strong bases only. Some things cannot really act as a nucleophile like DBU and DBN and so on. And some of the strong bases that cannot act as nucleophiles can be due to steric reasons, like butoxide. So those are strong bases. Now we're going to see what those do with primary, secondary, and tertiary. And then last, we're going to talk about solvents, solvolysis, water, methanol, ethanol, isopropanol, whatever kind of alcohols, or other weak base, weak nucleophiles with primary, secondary, and tertiary. All right? Okay, let's go. We're going to first do primary with those 4 classes of reagents A, B, C, D. Then we will do the secondary, then move on to the tertiary. That way we can see how each of these reactants vary in their reactivity depending on the reagent type. So it takes 2, especially in SN2 and E2. The rate equation has both the substrate and the reagent. So therefore, both of those are important. For all of these reactions, the leaving group ability would also depend on the pKa. So the leaving group ability would affect all of them. pKa is low for the conjugate acid, and the conjugate base, which is going to be the leaving group, in this case, let's say iodide, bromide, chloride. I also threw in an OTS, even though it's not an alkyl halide, just for an example. So all of those leaving groups, the leaving group ability is directly proportional to the pKa. So iodide is a better leaving group because the pKa is lower for HI. Then it would be HBr. So Br would be the next best leaving group among the halogens. And then it would be the chloride. So that would be the next best leaving group. So iodide is a better leaving group than bromide. Bromide is a better leaving than chloride. Fluoride is not really good. It's 3.2 pKa. It's not a good leaving group. This OTS was -2. So that is also a very good leaving group. All right, let's start. Primary and kick it out from the backside. So this is a textbook example of an SN2. So anytime you have these Top Gun nucleophiles, you are going to get a backside attack and SN2. You never see E2, SN1, E1 with those really good nucleophiles. So now your iodide leaves and you will replace that with a sulfur. Because this is primary, we don't see any chirality because you have to have two hydrogens. One of the most important things is to be able to recognize a primary. A primary alkyl halide would have two hydrogens attached to the leaving group. That's how you know it is a primary. There's no exceptions to that. Two hydrogens here, then you know it's primary. Okay, you should never kind of miss that because that's like the starting premise of this whole thing. So if you don't get this right, it's going to be downhill from there. Okay, so primary, two hydrogens. So you would get SN2. Then of course you would have your sodium iodide fall out. And so this is going to be for a very nice primary with a good nucleophile. Let's see what happens when you have a strong base, strong nucleophile, which is like a methoxy or an ethoxy. All right, let's look at B. Primary with strong base, strong nucleophile. As we said before, strong base, strong nucleophiles are small anionic, typically oxygen anions or nitrogen anions that can function as a nucleophile or a base, good nucleophile or a good base. Let's say we have methoxide. Now I have two primaries here, as you can see, both these carbons. So you take the alkyl halide, take the halide, draw a line to the carbon that is connected to. If you have two hydrogens, you have got a primary. Now this primary is pretty much linear. If you have methyl bromide, SN2 is the only option. So let's say you have a methoxide. It's going to be a super fast SN2 here. And you would get, let's say, a bromide being swapped out for a methyl methoxy group. Okay? And you would have sodium bromide fall off in the process. Now over here, it's still primary, but now you got lots of groups, you know, on the adjoining carbon. So it's a little harder for the methoxide to get in. So here you could have a E2. So if you have a hindered primary, that means you have other groups on the second, the beta, gamma carbons, and not really after this, just these, and especially the one next to it. hindered primary, then you could get E2 more than SN2. Now that is also something that you need to check out because it could vary, but this is a possibility. However, if you had a primary, then you would mainly have SN2. We don't really have to worry about E2. Primary with a small base and small nucleophile. If you have the same, let's say, ethoxide or methoxide, or some base here, and you have a hindered primary, you could get E2. So you have your base, which is your methoxy, come in, pick up that hydrogen, and make a pi bond and kick out the bromide. And that is a possibility that needs to be explored. All right. I'm just putting that in just so you know that those are possible. Plus, then your sodium bromide or iodide or whatever falls apart. All right. Moving on to the next bucket, we got DBU, DBN, third butoxide. What are we going to get? Let's say we are going to use third butoxide. What would be our major? We're basically focusing on major. So here, let's say we have a very bulky base. It's an alkoxide just like these, and it's got 3 lone pairs and an oxygen, but it behaves very differently in this case. The major reaction is from this pulling off a hydrogen. Why is that? That's because this is so big that it cannot get in for a backside attack. Even these hydrogens are going to repel that, and it can't really get in here. So therefore, the T-butoxide is going to go in and pull off a hydrogen that's then going to take off that chloride. So you have 2 hydrogens, and neither one of them can be pulled off, and you are going to get an E2 for the major. You would have a minor SN2, but E2 would be more than SN2. And in the SN2, you're going to get a backside attack here. It could be something like close to 80 and close to 20. So it's a lot here than here. Those are the 2 possibilities, E2, major, or SN2. So major, and this will be minor. Let's look at the last one, weak base, weak nucleophiles. This we typically use water, we used methanol, ethanol, solvolysis type reactions. What would happen? Would you get an SN2 or an E2? You need anions typically for, kicking out a group backside or pulling off your beta hydrogen and making an alkene. You need anionic compounds. If it is neutral, your neutral compounds are not strong enough to do that. Let's say we have methanol. This is neutral. It's only got 2 lone pairs, not 3. It's not really a heavyweight, strong nucleophile. It's also not a base. It's already protonated. If it picks up another proton, it's going to be positive. So it really loves to be neutral. However, it's slightly ionizing, and so it's going to rattle that bond and make a carbocation. Can you make a carbocation on a primary? I know it violates all of the rules, but you have to first see what the neighboring carbons are doing. So let's say this is going to be a very temporary intermediate, very, very temporary. Then if you have a neighboring hydrogen there that can move over and stabilize it, then it's going to do that in a heartbeat. It's going to do a rearrangement ASAP. So this is a very temporary, I will put temp, intermediate, and this is going to be the intermediate that you're going to be seeing floating around in the solution for a while. What happens to this? Well, this weak nucleophile can zap it and then you can get deprotonation of that hydrogen to give you an ether. Now, all of this could happen if you also had water instead of methanol. If you had water, you had hydrogens on both sides, so this would end up with an OH, and you get an alcohol. So basically, if you do solvolysis with an alcohol or water, you'll get an oxygen, and you'll get an R group or a hydrogen. And you will get, let's say, your OTS minus fall off with this, and that will be your anion there, and then that gets solvolized and washed out with workup. So this is a really good setup here to show you how your reactions are going to change depending on what's in the bucket. So this is for primary. So in summary, for a primary, when you have a really good strong nucleophile, SN2 backside attack. If you have a small, strong base, strong nucleophile, it's going to do SN2. That would be your major. And typically, I mean, almost 90% major, very big major. E2, minor product. But if you have a branched primary, it could have more E2 than SN2. The percentages here would depend on the substrate and the size of the base and the size of the branching, but you could have a mixture. If you have a strong base that's not nucleophilic, really strong, like DBU, DBN, third butoxide, they don't do backside attacks because it's too crowded here for major. So then they are going to go in and pick up your hydrogen next door and give you a nice alkene. Now, there is also a chance they could do a primary attack here, but that would be a very minor product for third butoxide, not for DBU, DBN, or even hydrides, or even LDA and things like that. They don't do SN2. Okay. If you have a leaving group, let's say, it could be an alkyl halide, bromide, chloride, or iodide, and you put in a protic solvent, weak nucleophile, weak base, that is going to rattle that bond, ionize it, and rearrange to the most stable carbocation possible, and then you're going to do an SN1. Whenever you do an SN1, there's always a possibility of doing an E1. However, the major product would be SN1. And I'll write minor E1 where you get a double bond right here, but that's going to be a very minor E1. Let's move on to secondary. Let's look at what a secondary alkyl halide would do with each one of these reagents. We got 4 buckets for you. We're going to just toss in one of them from each bucket with a secondary and see what happens. So how do we identify a secondary? That's really key to these reactions, being able to identify whether it's a primary, secondary, or tertiary. If, let's say, you have 2 R groups on the carbon that has a leaving group, a halide, like a bromide, iodide, or chloride, some halide, and you only have 1 hydrogen, that is going to be a secondary. 2 hydrogens, primary. 1 hydrogen here is going to be secondary. Okay, so that's really important. You put your finger on your halide, go out there. If there are 2 R groups, then obviously the third group out there is going to be a hydrogen, and the fourth would be your leaving group. If you have a secondary and you have a strong, good nucleophile, you are going to do a backside attack, because the strong nucleophiles that are here on top are not basic, so they don't do E2. The ones at the bottom, when they have a higher pKa, they could be basic. So the pKa is typically lower for really good nucleophiles, so they're not basic. So they are going to come in. In this case, you are going to have a S, and you're going to get a backside attack. So the first thing to do is identify whether it's a primary, secondary, tertiary. You have only one hydrogen, that's secondary. You have a good, strong nucleophile. What are you going to do? Kick it in the back. Backside attack. So that is going to come in, and here is your S, and so it's going to come in, attack from the rear, and kick it out. So whenever you have a chiral center, you can have an inversion of configuration. So your nitrogen here, well, let's draw out the Lewis structure here, and here is your positive and a negative and a negative, so overall minus, and sodium plus. So it's like a really nice, like a cigar shape. It has no steric at all. Comes in, attacks from the back, and kicks that out. So now you lost one of those lone pairs, and so your one lone pair, and then the remaining nitrogens are over here. So that's your N3 acid. And of course your sodium and then your chloride fall off together, which is good because that's going to drive the reaction forward. Now whenever you have a good nucleophile, the reactions have been found to be much faster in aprotic solvents. And we had a list of aprotic solvents, just look them up. And aprotic solvents that are polar are the best. DMSO, DMF, and so on. Let's say you have DMSO or DMF, and those are the good ones. Whenever you have methoxides, hydroxides, well, they come with the accompanying solvents. The solvent for methoxide would be methanol, for hydroxide would be water, and so on. For potassium T-butoxide, it's going to be T-butanol, and so on. Here the solvent is the reactant. So let's look at this. Obviously, sodium hydroxide is a solid. You need some water to dissolve it. And sodium hydroxide is one of the smallest bases. Does it do any SN2? Turns out no. It still does an E2 because bases, love protons A. 2, secondary is a lot more sterically hindered than primary. So if you have even a small base, it's going to go for the beta hydrogen. Now there are two of them. There's one here, and then there are two here. Which one is it going to go for? Is it going to go for the one that has an ethyl group or an alkyl group on that carbon, or is it going to go for the one that has two hydrogens here? So the more substituted alkene, in this case it's going to be 1, 2, 3 tri-substituted alkene, is going to be the one that's going to be the most preferred. That's going to lower the activation energy of the transition state. So you're going to go after the hydrogen that's on the most substituted carbon. That's called Zaitsev. And so your sodium hydroxide would pick up. That's your anion. It's got 3 lone pairs, and so it picks that up. Those hydrogen electrons are given to that carbon, which then makes it too many for that carbon because it has also a hydrogen that we haven't drawn here. So then it's going to kick out the bromide. So you would have an alkene forming, and the alkene is going to be always the more substituted. And that's the Zaitsev rule. So your water then comes out as a side product, plus your sodium falls off with the bromide. So all of these things happen simultaneously. It's concerted. So that's Zaitsev rule for you. Let's look at what happens when you have a good leaving rate. This is a mesylate, so instead of a toluene, you have a methyl. That's the only difference. So here you have a huge base. This is never going to act as a nucleophile, so there's no backside attack with this. This is going to be pulling off a hydrogen and running off. So let's look at this. It never pulls off the hydrogen on the carbon that has the leaving group, because if you have an anion here that's on a different plane, it cannot really kick out this mesylate. So never deprotonate the hydrogen that's on the carbon that has the leaving group, never. The only time you do anything here is when you have a nucleophile, you do a backside attack. That's it. Rest of the time, you work with your beta hydrogens. All right, so how many do we have here? Well, we have one here, and 3 here. All these 3 are identical. But are these hydrogens identical? Let's look at that. Now, this is a chiral center. So therefore, these hydrogens are prochiral hydrogens. These hydrogens are different. They have different environments. This one's on the same side as this estrone, and this one's on the opposite side. Now you know you can rotate them as well. And that's what we're going to do. We'll label these HA and HB. It's right next to a chiral center, so they are different. This is, let's say this is HC. And all these 3 hydrogens are identical. They're going to be rotating. Which one is the best for this huge base to pull off? If it pulls off this hydrogen or this hydrogen, you would make an alkene here, and you would think, oh, that's the most substituted one, and that's the one that's preferred. But no, not really, because there's too much steric here. So therefore, it goes for the one that's the least substituted. So the base here is so bulky, cannot get in here. It can only get in here. So the major would be taking this base and taking this lone pair and deprotonating it. And that's going to run into this carbon because that has a polar bond. This is a delta minus, delta plus, but that's too many electrons for it, so it's got to kick this out. So when you have a very strong, large base like this, no SN2, E2 only. However, you do not get the Zaitsev product, you get the Hofmann product. That means the less substituted alkene is the one that's favored. In this case, you really don't have cis and trans. If you did, then it would be E over Z. So that's going to be your major. You would get a minor product, and that would be the most substituted Zaitsev product. And there, E would be more than Z because of the steric here. So this would be your minor product. That's more than that. To show why this is preferred over this, I would need to do a Newman projection. Unfortunately, I don't have space, but we've done that in the past. So the one that puts the ethyl away from the methyl group would be the one that's favored. Let's look at this. Here's water. You know, water is not basic. You know, it's really not very reactive. It's a weak base, weak nucleophile. It's in the D bucket. What does it do? Can it do a backside attack or pull off this hydrogen? Nothing of that sort. All it can do is kind of ionize this bond, rattle it a bit, make those bonds break, and temporarily they can break. And here, more so than ever, because if you have a intermediate that's a carbocation that's next to a pi bond and many pi bonds, you can have a lot of resonance going on, and you know, you can write out all those resonance structures. So you know this is stable. Now then, once this is kind of doing its thing and stabilizing it, the water can bam attack right here. And so you can have your water attack here, and that would be your major product, where your water then it can attack above or below, and they're both going to be different chiral or stereoisomers. So I'm just going to put OH2 plus, then you deprotonate that with another water, and you've done that a million times, and you'll get an alcohol, a benzyl alcohol there. Now this is going to be a very major product, but if you heat it up a lot, then you could get some minor E1 product. That's the story with all of them. Okay, so SN1, major, minor E1. Sometimes it could be a 90-10, or sometimes it could be like a 70-30. It all depends on who's there and what's happening and the temperature and so on. The more you heat it up, the more you get this. But if it's cold, typically you get predominantly your SN1 product. All right, so that's secondary. So secondary with A is going to be SN2, just like primary with A was SN2. Secondary with B, strong base, strong nucleophile, is going to be E2. Now that is going to be different from your primary. So, and then strong base, and typically sometimes bulky base and non-nucleophilic base is only going to do E2, and that would also be a Hoffman elimination. The small base, there's a Zaitsev elimination. When you have a protic solvent, weak base, weak nucleophile, that's going to ionize that center, secondary carbocation. In this case, really there's no rearrangement possible. However, resonance stabilization is huge here, and then you can have substitution or elimination. Typically substitution, way more than elimination. All right. Let's look at the tertiary, this bucket. What happens when you add A, B, C, D to your tertiary? So tertiary, all backsides covered, no SN2. Does that mean there's no reaction? It depends. If you have a protic solvent, let's say you are in a protic environment and you have a nice protic solvent, let's say you have HCN, then you can have SN1. And that would give you a carbocation, and you could then do a SN1. Okay, and put your cyanide right here. So always consider that possibility if you're in a protic solvent and you have like an acid or a something that can ionize a alkyl halide. All right, let's move on to our strong base, strong nucleophile. Here's an ethoxide. What are we going to do? Are we going to do a backside kick? This is tertiary, no backside. Okay, no backside attack on tertiary. You have a protic solvent and you have a base. Now, so does that mean that you can do this and this? No, even though you have a weak base, weak nucleophile, it's going to be completely overpowered by the strong base, strong nucleophile. Okay, it's like this huge, gigantic guy. You're not going to worry about them. Okay, just worry about the big guy or the strong guy with more lone pairs. So this guy is going to go in and, well, can't get in here. There's too much stuff. He's going to get whacked out. So then it tries to go in and grab a proton. And let's say, okay, I'm going to make ethanol and be happy. So now there are lots of hydrogens for it to abstract. This is your center. Right next to that, there's a carbon here, carbon here, carbon here. 3 beta carbons. So let's say I'm going to label this A. And here are possibilities HB, HC, and let's say here's another one, HD, and there are 3 of them. Which one is it going to go for? It's all really confused. It's got all these hydrogens to pull. However, this is a really small base. It can pull whichever one is going to bring the energy of the transition state down. So you want to have the maximum number of substituents possible on that incipient pi bond to support it. And let's say which one's going to give you the most substituted. So the more branching you have, the better it is for E2. The less branching you have, the better it is for SN2. This carbon is branched. If you form a pi bond here, you'll be tetrasubstituted. Can't get better than that. And if you form a pi bond here, you'll be disubstituted. So it's going to go tetra more than tri more than di. Okay, so let's pull this off. literally take this hydrogen off, put that pi bond, make that pi bond with those electrons. OTS has to leave because there's too many things there, and you are going to get a tetrasubstituted alkene, and that would be your major. In this case, it really doesn't matter whether it's E or Z because these are identical. So if you pull off HA, you're going to get the most substituted, tetrasubstituted A product. That's going to be the highest amount. Now, you could pull off B or C and get a trisubstituted, and D and get a disubstituted. Let's look at which one of these prochiral hydrogens is the best one to abstract. So for that, we're going to draw a Newman projection looking at it from this side. So this is your dot carbon, and that's going to be your circle carbon. The dot carbon is going to have this ethyl tail going up, and then your HB is going to be to your right, and your HC is going to be to your left. This is going to be coming out and away, and HC is going to be to your left here when you're looking at it like that. So wedge would be to your right, and dash would be to your left. And this carbon, when you look through, we'll draw that as a circle. You can see the OTS is going to the right. Methyl is going on the other side, CH3, and then down is your isopropyl group. Now, do you want to do an elimination taking off this HC and making a pi bond here? Or do you want to do an elimination where you have the HB here and eliminating with the OTS? That's difficult to see until you draw it out. So if you rotate this, that's your dot, and that's your circle at the back. At the circle at the back, you're still going to have your OTS, your methyl, and your isopropyl. This steering wheel, you're going to turn 120. That would be HB then. HC would go here, and your ethyl would come over here. Which do you think is better to form a transition state? Look at the sterics of this. So in both cases, you're going to do the same thing. You're going to take your base, which is your ethoxide, pull off the hydrogen. Those are going to go into that carbon here and kick out that OTS. You could do that with HC or HB. So really, there's no difference in the mechanism. Which one do you think is going to have a lower energy transition state, which means your activation energy is lower? Look at the sterics. Here's a huge bulky group butting heads with another bulky group. That's a lot of steric. So you don't want this. This is very high energy. You don't see that over here. Your isopropyl is surrounded by two hydrogens. It's true there's a methyl and an ethyl there butting heads, and they are gauche. But that's not as bad as having an ethyl and an isopropyl gauche and butting heads. Okay, so therefore, pulling off HC is better. And so you would have a trisubstituted here. When you put your double bond here, you are going to get an ethyl and a hydrogen HB on one side, and a methyl and an isopropyl on the other side. This is going to be the second best trisubstituted alkene. So this is C, this is going to be trisubstituted. The next one would be your B, and that would give you a trisubstituted as well. However, it's going to put the isopropyl and the ethyl on the same side, which is really not that great. Okay, and the least favored of all of this is going to be the one where you're taking off the HD, and that's going to give you a disubstituted. So this is, let's say, B, and that's also tri, because you're pulling off the B proton. And if you pull this off, you would get isopropyl and that's going to be D, disubstituted alkene. So you get a whole bunch of alkenes, and the major would be this, and then the tri, and then the di, And in the tri-substituted, E would be more than Z. Even in the product, there would be steric here. Okay, so that's for small base. So if you have a small base and a alkyl halide or a leaving group here like this on a tertiary, you have lots of possibilities because you have lots of neighboring protons. The one that gives you the most substituted, in this case tetrasubstituted alkene, would be the best or the most preferred. Next would be tri-substituted, and we have two candidates for that, HC and HB. Do we randomly pull them off? No, we have to look at the transition state and the sterics of this. So if you draw a Newman projection, it's much more obvious which groups are butting heads. So if you take this and draw a Newman projection through here, you can see that if you pull off HC and create a double bond through this dot and circle, you would have the big groups on opposite sides, which is going to give you a nice E or trans alkene. The reason for that is the big groups are away from each other. If you pull off the B hydrogen here, the B hydrogen is going to put the isopropyl and the ethyl next to each other, and there's going to be a lot more steric there. And so that is going to give you a Z alkene. So I would say A more than B more than C more than D. Okay, in that order because of the stability of your transition states. Now I'm going to take this off and then we will try a tri-substituted with a big base. Let's look at this reaction here. We got a tertiary. How do we know it's tertiary? Now hydrogens, 3 R groups. And we got carbu, a huge base. And these are going to do basically only E2 on tertiary. Even small bases, as you said, are going to do E2. So you don't even have to mention this. The larger bases are going to go straight for the E2. So then when you're doing an E2, you just find the carbon that the halogen's connected to. Find out who the neighbors are. Neighbors are extremely important here. You got neighbors here, really substituted. We got neighbors here, and we got neighbors here. Which one is it going to go for? Well, it's huge. It doesn't like to be whacked by all of these groups, so it's not going to go for the most substituted. Goes over here, oops, and just plucks out that hydrogen here. No steric, no one's going to beat it up, and so that's the one that it's going to go for. Another thing that we have to remember, that when you have a chair, your elimination is going to be diaxial. So we got to put the chlorine in the axial position. Let's draw the other chair going down here. Let's land it up. Dot and dot. It's been a while since we drew our chairs. And there you go. Now your chloride is going to be down and your methyl is going to be equatorial. And this methyl on the carbon 2 that was axial is now going to be equatorial. So you have a hydrogen here that you can abstract. Let's call this A, HB, and then you have 2 hydrogens here. We can only do the axial hydrogen, so I'm going to draw that as C. So we have 3 possibilities. Now, if you had a small base, you would go for the one that's more substituted, then this, and then this. If you have a huge, enormous base, you'll do the exact opposite. You're going to go for the Hoffman elimination. So you will pull off this hydrogen with your carbu, and that's going to make a pi bond here and kick out that chloride. So you would have a 6-membered ring with a alkene that is exocyclic. And over here you'll have a methyl group, and this methyl group is going down. So that's going to be your major. Your second major is going to be the less substituted carbon here more than this. So here you are going to pull off this and you would have a methyl here. So if you were to draw a double bond right there, you are going to have a methyl here and a double bond right there and your methyl here would be right down here. The last one would be your double bond right here between the methyl and the other methyl. So you would have this tetra-substituted alkene, just because of the sterics. So di more than tri, more than tetra, which is exactly the opposite of what we did with a small base. You have to really pay attention. Also, if you have neutrals in the presence of anions, ignore them. They're not strong enough to do anything compared to these. So these guys do all the work, the anions. Okay, they are your workhorses in all of the E2 and SN2 reactions. So here's a nice E2, and it is going to be a Hofmann. This is also a nice E2, but it is going to be a Zaitsev. Let's look at this tertiary here. So tertiary anaprotic, and this is just, it could be any alcohol, could have any number of carbons here. It doesn't really matter. Just drawing one of these out. What does this do? Does it do a kick on the back? No chance. It's not strong enough. Does it pull off your beta hydrogens? No chance. It's not basic enough. So it's a weak nucleophile, weak base. All it can do is rattle that bond and create a carbocation right here. Now that carbocation has a lot of possibilities. It's got really good neighbors here. So that's your neighbor, HA. Here's another nice neighbor with 2 hydrogens, HB. And let's say HC. And here's another one, HD, and there are 3 of them. The weak base can attack this and do an SN1. Always SN1 is more than E1. So let's first do the SN1, where this is going to attack right here. That is going to give us a substitution product where you have all of the R groups the same, except this is going to be up and down attack. So I'm going to put a squiggly line and say you're going to get this ether, SN1. If you start with an alcohol as your weak nucleophile, you get an ether. If you had water, you get an alcohol. Now, for the E1 reaction, what are the possibilities? It's going to do Zaitsev. Always E1 is going to be Zaitsev. And always SN1 will be more than E1. Now, if you really heat it up, E1 can go really high and exceed the amount of SN1. But typically SN1s are a lot more than E1, some like 90% to 10% in a lot of cases. But as I said, it also depends on the temperature. More substituted is preferred. This is going to be tetra. This is going to be tri. This is going to be di. Here you have choices, and in this case, really you don't have to draw a Newman projection because the one that gives the E is the one that's going to predominate. So always E more than Z whenever you have choices. Because in the Z there's more steric. So let's just start with A. So in A you're going to get your double bond right there. So this is going to be more than a double bond right here. That's your tetra. That's going to be more than a tri. That is going to be E more than Z. This is a hydrogen, so this is opposite. That's going to be more than a Z, where you have both the big groups on the same side. So in addition to these E and Z, these are tri-substituted, both of them. You can see 3 R groups on the pi bond. You could have a little bit of a di. So I'm just going to put that over here, more than a di. Okay, this is going to be very minor. All right, so in conclusion, you can see that you can get all kinds of reactions. It depends on whether your substrate is primary, secondary, or tertiary. And it depends whether your reagent is a strong nucleophile, strong base, huge base, or a weak base and weak nucleophile. And they have completely different mechanisms because of the physical organic principles that govern reactant pathways and the energies. So therefore, when you have a tertiary with A, you are going to get no SN2. If it is protic, then you will get, or acids, then you will get SN1. If you take B, then over here, you're going to get mostly your Zaitsev, E2. The amount of SN2 here would be negligible. For tertiary, it's all E2. And if you have strong base, you don't even have to talk about SN2. There is no minor SN2. When you add strong and large bases, you're going to get E2, but you are going to get E2 that is Hofmann. If you have a tertiary with weak base, weak nucleophile, you'll have SN1 more than E1 typically, and the E1 is always going to be Zaitsev. I'm just going to put Zaitsev, Z. All right, so in conclusion, I would like to say that you really cannot generalize and say, you know, this is what a nucleophile is going to do, or this is what a base is going to do. You really have to look at the substrate and sometimes even the solvent to decide what the pathway is going to be. It all depends on sterics, electronics, and the energetics of these reactions. All right, I'll talk to you soon. I'm sure you have a lot of questions, and I'll be happy to help you. Talk to you soon. Bye.